Alright guys, so we've derived the kinematic equations before using a velocity versus time graph. Now we're going to talk about getting the kinematic equations actually using calculus. So remember, the kinematic equations are for constant acceleration. So we'll be real creative and say we have a constant acceleration a that equals some value that we'll call a. So if we want to derive an equation for velocity, remember that v is the integral of a with respect to t, right? So velocity is the integral of acceleration with respect to time. And of course, if we evaluate that integral, then what we're going to get is at plus c. And as we said earlier in class, c in this case is just the initial velocity of the object. So what we end up with then is that v equals at plus v naught, or the more traditional way of writing it, which is that v equals v naught plus at. And so that is our first kinematic equation. Now we're going to derive our kinematic equation for position or displacement. So remember, position is always the integral of velocity with respect to time. So that's going to be the integral of v naught plus at with respect to time. So if we evaluate that integral, we're going to get x equals v naught t plus at squared divided by 2 plus c. And remember, in this case, like we also talked about earlier this week, c is x naught, the initial position. So we can rewrite that and rearrange it a little bit and get x equals x naught plus v naught t plus 1/2 at squared, and that gives us our position kinematic equation. Now, if we want it for displacement instead, displacement is just x minus x naught. So we subtract x naught from both sides, and we get delta x, because that's just x minus x naught, equals v naught t plus 1/2 at squared. And so there we have our second kinematic equation. Now we're going to derive a third kinematic equation using the first two. So the first one we had was v equals v naught plus at, which we have rearranged right here to say that t equals v minus v naught over a. And then our second equation right here, delta x equals v naught t plus 1/2 at squared. So what I'm going to do is I'm going to take this value for t, and I'm going to plug it in for t in the other equation. So I'm going to end up with delta x equals v naught times v minus v naught over a plus a over 2, that's just 1/2 a, it also can be written a over 2, times v minus v naught over a times v minus v naught over a. I just wrote it out twice instead of squaring it. So that way I can see that this a and this a cancel. I get that 1/2 there. And now if I multiply both sides of the equation by a, I get a delta x equals, and I'm going to go ahead and distribute throughout these parentheses. So I'm going to get v naught v minus v naught squared for the first part plus v squared over 2 minus 2 v naught v over 2 plus v naught squared over 2. So I can go ahead and cancel out these 2's, and then I've got a v naught v minus v naught v, and I can get rid of both of those. And now if I multiply both sides of the equation by 2, I get 2a delta x equals v squared plus v naught squared. Sorry, that's v squared minus v naught squared, because I have a minus v naught squared right there and a plus v naught squared over 2 right here. Multiply both sides by 2 and it comes out to v squared minus v naught squared. Alright, so then for our final rearrangement we end up with v squared equals v naught squared plus 2a delta x, and there is our third kinematic equation. For our final kinematic equation we're going to use the first two again, so I've taken the first one and rearranged it to solve for a, and then I've taken my second kinematic equation right there and I'm going to plug my value for a into that other kinematic equation, and so I get delta x equals v naught t plus 1/2 times v minus v naught over t times t squared. So that this t and that squared cancel out. If I distribute things in there, I'm going to get delta x equals v naught t plus vt over 2 minus v naught t over 2. Since v naught t minus v naught t over 2 is v naught t over 2, I get delta x equals v naught t over 2 plus vt over 2. By slightly rearranging the equation, factoring out the 1/2 and the t, I get delta x equals 1/2 v plus v naught times t. So there is our fourth kinematic equation. And on Monday we'll talk about how to use these in class.